I'm glad to welcome you to this tutorial, Completeness, Recall, and Negation in Open World Knowledge Bases. I'm Simon Razniewski, and this is a joint tutorial with Hiba, Arnaout, Shrestha, Ghosh, and Fabian, Suchanek. And yeah, if you have any questions or comments throughout the tutorial, don't hesitate to unmute yourself and speak up. You can also write in the chat. However, we as speakers might not see it immediately. You can also write in a Slack channel, so we are monitoring the different communication platforms, but the easiest is probably to just speak up. Our tutorial today is divided into 5 parts, each taking roughly half an hour. So I'll give now the introduction and the foundations of the topic. And then Fabian will talk about predictive recall assessment, Shrestha about counts from text and knowledge bases, Hiba specifically about negation, and then I'll last talk about relative completeness and wrap up the tutorial. So the topic of the tutorial is called limits of machine knowledge. So what do we mean by machine knowledge? Machine knowledge is nowadays deployed in many places and can be seen in many applications. But one particularly prominent way is in search engines. So in traditional way search engines are used, they do a keyword match. So here physics Nobel Prize winners, Google search engine would find documents that contain these terms and then rank these documents by traditional scores like PM25 or so. Nowadays, the paradigm of search and question answering has much fused. So if you go to prominent search engines nowadays, you're not just getting documents back, but you directly get structured answers which come from a knowledge base, which come from machine knowledge. So for example, here for the physics Nobel Prize winners, there's entity disambiguation happening in the background. So the entity is Nobel Prize in physics, and the relation is identified winners, and then we get a listing of entries here along with the years. We can also see that here for Marie Curie prizes, again, disambiguated as the subject awards for the entity Marie Curie, or I'm not entirely sure how Google represents its knowledge. It's unfortunately closed source, but machine knowledge is awesome. So it's a reusable and scrutable asset for a range of knowledge-centric tasks: semantic search and question answering, text analytics. It's also widely used for distant supervision for machine learning to get training data in the first place, for data cleaning. There are impactful projects at public and commercial players. So Wikidata most prominently in the public domain, and major tech companies have their own KGs. And all this is strongly rooted in knowledge representation, semantic web communities. So for all the works on knowledge representation, vocabularies, ontologies, and so on. Machine knowledge is awesome. However, it is generally incomplete. So I apologize that this cannot be reproduced anymore. That's what I got 3 weeks ago in Google when I asked for Marie Curie prizes. It gave me a list of prizes, but it missed the ones that most obviously are the important ones. Marie Curie won the Nobel Prize, not just once, but twice. And this was not shown in the interface. Similarly, if you go to public knowledge base Wikidata, you search there for the Semantic Web Journal, you'll only find 84 articles ever published in there. You'll find that the most cited papers from KRR works have less than 3 citations. So clearly, there's a big hole in terms of knowledge coverage. Machine knowledge is also one-sided. So what we find in popular knowledge base is that Tesla received the title of the IEEE Fellow. Vietnam is a member of the ASEAN. The iPhone 12 has a 12 megapixel camera. What we don't find are the salient relations shown at the bottom here. So Stephen Hawking and the Nobel Prize, what's the salient relation there? Any guesses? Just you can write in a chat or just speak up. Did he design the Nobel Prize? Did he fund the Nobel Prize? What's the relation between Stephen Hawking and the Nobel Prize? Never got one. Yeah, correct. Notably, the famous physicists, black holes and everything, despite all his fame, never got the Nobel Prize. Similarly, Switzerland and the EU, what's the prominent relation there? Membership, partnership, neighbors, enemies, allies. Well, a salient relation there. Switzerland is not a member of the EU. And similarly for the iPhone 12, the notable thing that you find in all forum discussions about is it doesn't have a headphone jack anymore. So knowledge base contain the positive knowledge shown at the top, but not the salient assertions we see at the bottom. Why is this problematic? It's problematic at the query time. Decision making many areas is more and more data driven. So if we execute analytical queries, they paint the wrong picture of reality. So we may assume that the publication venue is too small. If we search for instances, we simply get wrong results. We may wrongly assume that someone never published in the Semantic Web Journal. It's problematic in data curation because we don't know how to prioritize our efforts. So in most data curation efforts, there are humans in the loop at one stage or the other, either doing directly the data entry or deciding which domains to crawl and so on. So without knowledge about completeness, we don't know, should we spend effort on completing the Semantic Web Journal or TKDE, for example? And we may duplicate efforts if we don't keep track of what is completed. And the negative part is especially relevant in summarization and decision making. So these are examples from the consumer domain. If you want to book a hotel, booking.com gives you a long list of positive features that apply to a certain property. So this hotel has towels, this hotel has toilet paper notably. It also has a neck massage, but the most salient thing for many of us computer scientists, I think, this hotel doesn't have free Wi-Fi. And we have to spend effort here seeing, okay, there's paid Wi-Fi, then inferring there's probably no free Wi-Fi, but the salient negation is not explicitly here. And similarly on the right-hand side, so we see all these positive features that the iPhone 12 has, portray lightning with 6 effects, but we don't see the salient things that it doesn't have, no headphone jack. So the topic of this tutorial is how to know how much a knowledge base knows, and to disassemble this question a bit. So how to reverse generate to techniques for knowing this, and how much knows refers to a dimension of completeness or recall or coverage, which we use largely synonymous in this tutorial, and both for the purpose of bookkeeping, so keeping track of what is entered, and for estimation, so which goes beyond keeping track of what we entered, but also making statistical estimates of how much is there or how much is missing. And knowledge bases we interpret liberally here as any storage of general world knowledge. And so what we offer in this tutorial is, in the first part, logical foundations. So the setting and the formalisms to describe how complete a knowledge base is. In the second part, statistical methods for prediction based on supervised learning, based on other statistical interesting techniques. In the third part, count information, especially a valuable cue for assessing completeness, how we can identify these inside KPs and link them, and how we can extract them from text for the same purpose. In the fourth part, negation, how we can derive salient negations from incomplete knowledge bases. And in the fifth part, relative recall. So how can we assess recall even if we don't have a gold standard notion? And the general goals are to give a systematic overview of the topic and its facets, to lay out assumptions and strengths and limitations of the different approaches, and to provide a practical tool suite and recipe for recall assessment for custom knowledge bases or custom slices of existing knowledge bases. And this tutorial touches on many research domains, notably semantic web logic, statistics, machine learning, NLP. We'll generally assume basic knowledge with concepts, but where needed, we'll introduce them also in more detail. And last, for the introduction, let me clarify what this tutorial is not about. So it's not about knowledge-based completion. Completeness is a property, completion is a task. Knowledge-based completion is concerned with how to make a knowledge base more complete. And the two topics are closely related. So we need an understanding of completeness to know when or when not to employ completion techniques. However, because knowledge-based completion is not evenly open-ended, so if you employ completion techniques, they will give you a ranked list of suggestions what could be added in a knowledge base, but we need an understanding where to stop with this. So on the right-hand side, there's an example here. If we ask the typical statistical method for Beatles members, it will give a ranked list with likelihoods, some of them correct in green, some of them incorrect in red. And without understanding of completeness, we wouldn't know where to threshold these lists. At the top right, we also see a prominent model trans-E for that purpose. However, the two have also marked differences. So completion is a heuristic and error-prone process that is not always desired. So sometimes we just want to know how complete our knowledge is, but we don't want to embark on this error-prone process. And sometimes completion is not even actionable. So for example, we may know that Aristotle's children are missing. He had children, but to the best of our knowledge, the names of the children are lost in a historical record. And there's a vast literature on knowledge graph completion, missing value imputation, and so on. So I just link one survey in the bottom here. And the slides you can find on a tutorial homepage, so to recover all these links. So much about the introduction. Are there questions, comments at this stage? If there aren't, then I'll move on to the logical foundations. So the definition of knowledge base we'll work with in this tutorial is we assume a standard definition, a set of entities E, a set of literals L, a set of predicates P. Notably, predicates can be both positive or negated properties. So a predicate can be both born in or not won award. Then we say that an assertion is a triple SPO of an entity, predicate, and an entity or literal. And practically available knowledge bases that we work with, we call KA for knowledge base available, are sets of such assertions. And for each available knowledge base, conceptually, we say that there's also an ideal knowledge base which represents the complete information from the domain of interest. So this is called KI, and the available data we have is normally incomplete. So we say that KA is a subset of KI. And here's an example of knowledge that could be stored in these knowledge bases or knowledge graphs. So taxonomic knowledge that Marie Curie was a physicist, that physicists are scientists. We can store factual knowledge that Marie Curie was born in Warsaw, that she lived in Paris, or that her place of birth was not in France. We can also go beyond triples. Again, that's standard in a knowledge representation community by using reification or event entities. So if we want to store the date, the place, and the person concerning the discovery of polonium, we can introduce this additional entity 1, 2, 3, 4, 5 here to store this information. And we can also go beyond this more prominent topics to long tail and expert knowledge, like the atomic number of polonium or the half-life of polonium. Knowledge base history in one slide. Again, I think the audience here is very familiar with this. One of the early projects there is Psych, which tried to codify both rules. Humans have a mother and father, and mothers are singular, but also factual knowledge. Around the same time, in the linguistics domain, WordNet emerged, which tried to originally organize nouns and later also other parts of speeches, so that guitarists are players and musicians. But the term player is ambiguous, can also refer to an athlete and so on. So these were manual efforts at small scale. Around the 2000s came the Wikipedia revolution, where suddenly it's millions of people curating knowledge. So this was all human efforts. Although Wikipedia was originally not much in structured format. So around 2006 came automated and human in the loop approaches, notably Yago and DBpedia, which extracted structured information from Wikipedia and turned it into machine readable format. Freebase around the same time enabled large scale structured knowledge curation for humans. And then other early commercial players, Wolfram Alpha, Google Knowledge Graph, and nowadays we find knowledge base in most big tech companies, but also beyond. So from Amazon to Bloomberg to Alibaba and so on. Knowledge bases are huge. So Wikidata, the largest open one, has close to 100 million items, 1 billion statements, and Google has around 5 billion items, almost as many items as there are humans in the world, 500 billion statements. And major use case I already mentioned are in search and question answering, language understanding, distance supervision, data cleaning, and so on. However, no matter how big these resources are, they are incomplete, and incompleteness is inherent. So sketching here very simplified a knowledge-based construction process. We have some reality at the top left, which gets represented in documents. And on these documents, knowledge-based construction methods are running, which can be either automated methods, IE methods, or can be humans which are reading these documents and then codifying the structured knowledge. And at the top right, we arrive with structured information. Einstein won the Nobel Prize. Einstein won the Prix Jules Janssen. Einstein was a friend of Max Planck. And there are several stages in this pipeline where incompleteness creeps in. What are your suggestions? Where does incompleteness come from in this pipeline? Please write in the chat or just give your suggestions by voice. Suggestions where, why does the structured information at the right-hand side not capture reality completely? Well, then let me give suggestions. So first one is that the sources themselves are an incomplete representation of reality. So what we see here, the document says Einstein received the Nobel Prize, the blah, 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 and several others. So the several others means he won actually more, but I see a suggestion in the chat. Magdalena, both blue arrows, neither documents are complete. Exactly, that's the point. Not the extraction from them. Exactly. These are two major points. Yeah, the documents are not complete. The extraction from them is not complete. So yeah, the source doesn't contain all the information from reality. You also got the honorary doctorate from Madrid, the Benjamin Franklin Medal, and so on. And this is even more severe for negative information. So sources hardly talk about negative information. He didn't win the Nobel Prize for the relativity theory. And negation is notably quasi-infinite, depending on whether you assume a finite domain or not. So you also didn't get a Nobel Prize for electric toaster or anything else. But obviously we cannot enumerate all these negations, and most of them are nonsensical. Then, as Magdalena said, the other blue arrow, the extractors are imperfect. So the document on the left-hand side also mentions a Copley medal. This is not shown on the right-hand side. The extractor just missed it. This applies both to human and automated extractors. And also the friend relation is actually not correct. So he won Max Planck medal. That doesn't mean he's a friend of Max Planck. And even if extractors were perfect, another reason is that they are usually resource bounded. So we have only finite time for human curators, or perfect extractors can only go to a limited set of websites. So yeah, these are 4 general reasons why knowledge base completeness is inherent. And the resulting challenges for knowledge base are that available knowledge bases are incomplete, not just they are a subset of the ideal, of the complete information for the domain of interest, but usually they are a much smaller subset. So they're considerably incomplete. And second, the negation I already mentioned. Documents hardly mention negation. Negation is quasi-infinite. This is hardly represented in knowledge base. So the negative part, I write this here as Ka minus, is close to empty in most knowledge bases. So to mention one topic that probably everyone here is well familiar with, what are the formal semantics for incomplete knowledge bases? We have the closed and the open world assumption. So if you have this relation here, people winning certain awards, we can have different semantics for answers. So another closed world assumption. Brad Pitt won the Oscar. The answer is yes in both cases. Closed and open world assumption because that's in the data. But when we asked, did Brad Pitt win the Nobel Prize, and under closed world assumption, the answer is no because it's not in the data. Under the open world assumption, the answer is maybe, because we don't assume that we don't assert that the data is complete. And traditionally, databases use the closed world assumption when we're working in limited domains like a company or so, and knowledge base and the semantic web necessarily operate under the open world assumption. However, the open world assumption, if we take it too literally, gives somewhat counterintuitive results. So another open world assumption, if you asked, was Game of Thrones directed by Shakespeare, then Wikidata and similar knowledge base should say maybe, because it's not in the data, but it could be still true. Does Brad Pitt attend KR? Well, again, if you have the guest list and we don't assume the closed world assumption, then anyone not on the guest list could still attend. So the answer should maybe, is Trump a brother of Kim Jong-un? So whether you spot similarities or not in their political style, the answer would again have to be maybe. And that's not really the world-aware AI or practically useful paradigm. So the logician's way out is completeness metadata. So we need the power to express both the maybe and the no for assertions. So a paradigm that bridges open and closed world assumption. And that's actually an old idea to use completeness assertions as additional metadata to assert where the open or the closed world assumption holds. So here we have again our table of awards, and we can additionally have some metadata which says, okay, we have all the Nobel prizes in this table. And if you have this additional completeness metadata, then our set of answers to queries becomes 3-valued. So we can again say, Brad Pitt won the Oscar. The answer is yes, because that's in the data. Did Brad Pitt win the Nobel Prize? The answer is now no, because we have this additional metadata which says all Nobel Prizes are there. Did Brad Pitt win the Turing Award? Then it's not in the data. We don't have metadata which says Turing Awards are complete. So here the answer is a maybe. And so more abstractly, the power of completeness metadata is with this metadata, we know what the knowledge base knows. So we can assert locally that what we have available represents also what is true in the ideal state, in the complete state. And similarly for negations, if a statement is absent from a knowledge base, then it's actually really false. So locally, where we have this completeness metadata, if a statement is not in the available data, then the statement is actually false in reality. And formal view of completeness metadata. So this is a common syntax. We assert which relation is complete for which condition. So the one award relation is complete for all the awards that are Nobel Prizes. This implies a constraint on the possible state of the available and the ideal knowledge base. In particular, it can be interpreted as a tuple generating dependency. So whenever there is some name which won the Nobel Prize in the ideal knowledge base, then this statement should also be in the available knowledge base. And similarly for cardinality assertion, let's say how many statements are there. So if we say the Nobel Prize was awarded 603 times in reality, then this is a constraint on the ideal knowledge base. So the size of this relation for Nobel is 603. And now we can go to our available knowledge base and count. And if you find 603 entries of Nobel Prizes in there, then we can assert completeness for this part of the knowledge base, or otherwise we can at least assert fractional coverage or recall information. So maybe the 93% of the awards are covered. And that's grounded in number restrictions or role restrictions in description logics. And the problem that has been well studied is formal reasoning with this completeness metadata. So also called query completeness reasoning. So we have a set of completeness assertions for the base relations in our knowledge base or database, and we have a query queue, and we want to know what assertions can we derive for the result of that query. So the general problem is basically similar to algebraic computation of query results. So how do we propagate the completeness metadata through different sub-expressions of the query? And yeah, I mentioned this problem is well studied. So there's quite a set of works looking at different description languages, describing which part of the data are complete and focusing on different aspects, algorithms, decidability, complexity, and so on. What these works usually disregard is where does this completeness metadata actually come from? So naively, one can say that either data creators should pass this along as metadata while they create the data, or editors should add this in curation steps. And we actually find both happening to some degree in reality. So on the left-hand side, this is a screenshot from OpenStreetMap Wiki. where the editors are keeping track how complete data is in different districts of a city. So in Abington, the roads are dark green, so they are very of good quality. The public transit information is red, so that's not completed yet. And on the right-hand side, this is from Wikipedia. So here, for a table of compositions by Maurice Ravel, there's not just the information that these are compositions by him, but there's also this additional statement. This is a complete list of compositions, which again says, well, this is a completeness statement for this information. And there's also a tool available for Wikidata. So here's a screenshot from this tool where editors in a Wikidata-like interface can assert for sets of statements that now the set of values is complete. So this is, for example, for Donald Trump, for the children property, someone asserted that to the best of public knowledge, these 5 entries are all the children that Donald Trump has. And this can then be used in query answering. The but with these issues approaches is they require human effort. And soliciting metadata is more demanding than soliciting data. So if I ask you, tell me some children of Donald Trump, it's easier for you to go out and find some than to give this additional assertion that now these are all children. And similarly, in automatically created knowledge base, we do not even have editors. So once we use information extraction techniques or so. So in the remainder of this tutorial, we look at how to automatically acquire information about what the knowledge base knows. And the takeaway from part 1 is knowledge base are pragmatic collection of knowledge. So they're inherently incomplete and they hardly store negative knowledge. The open world assumption as the common paradigm is necessary on a semantic web, but if we take it too literally, it leads to counterintuitive results. And metadata about completeness or counts is a way out. And next, Fabian will show you how to use predictive models to derive completeness metadata. Thank you. And are there questions, comments, suggestions? Yeah, if you have questions, also if they come later, just write in Slack or write in the Zoom chat. I suggest we continue directly with Fabian's part now. Thank you.
All right. Very good. Yeah. Thanks for the first part, Simon. I'm going to follow up with the second part on predictive recall assessment. So this part is about how we can find out whether a knowledge base is complete. So given a knowledge base, how can we find out whether we are missing entities or facts or anything of importance? So I'm going to partition this into 3 parts. First, I'm going to talk about the basics, which is the prediction of facts. So there are mechanisms that can predict specific facts that are missing. And then I'm going to talk about, in general, the recall of facts. How can we actually figure out whether we have all facts that are of interest? And this, the last part is then about the recall of entities. How can we know whether we have all entities that are of interest? Let me start with the basics of predicting facts. So this is actually a very well-known and studied problem. So here's an example. So we stay with the universe of scientists of Steven Pinker. He's a psychologist, and he has a sister, Susan Pinker, and the mother of them is Rosalind Pinker, right? And so we know Susan is female, right? So then we can kind of guess, yeah, that Susan must be the sister of Stephen. Yeah? So we may be able to deduce facts that are missing simply from the relations in which these facts are appearing. So, and once we're able to predict such facts, it also means that these are the parts where the knowledge base is incomplete if these facts do not appear. Yeah? So that's a simple problem of fact prediction. So given a knowledge base, finding facts that are not yet in the knowledge base, but that are true in the real world. Yeah? And so this standard solution to this, or one possible solution to this, is to proceed by rule mining. And I'm mentioning this here just as an introductory element, because it's not the main part of this tutorial, but we need it for what follows later. So I'm going to briefly introduce the rule mining as a preliminary. So rule mining is the process of finding from a knowledge base rules such as the following. First one, for example, if somebody has a child and if somebody has two children actually, and the second one is female, then the second one is the sister of the first one. So that's the rule that would allow us to deduce that Steven Pinker has the sister Susan Pinker. Other rules: if you're married and you have a child, then most likely your spouse is also the parent of that child. And you see here that this rule is not always true. So it's true with a certain probability in the knowledge base and in the real world. So typically these rules come with a score. Other rules: if you're born in some country and that country has a certain language, official language, then most likely you speak that language. And these rules can obviously be used to predict facts. So if I don't know which language you speak, but you tell me you're born in France, then most likely you speak French. Or I don't know whether I don't know the parents of Susan Pinker, then these rules can help us to deduce probably that Rosalind is the mother of Susan. So this is one way in which this can be done. That's it's not main part of this tutorial. So I'm just briefly going to give the references of systems that can automatically find such rules. Such rules can be mined bottom up or top down. What does it mean? Bottom up means that we're going to have first rules that apply to only a single instance. For example, if your mother is Rosalind Pinker and you're Steven Pinker, then your sister is Susan Pinker. That's a rule that applies to just a single entity. And then you generalize this. You say, if you're a psychologist and you have a mother and you have and the mother has a daughter, then you are this. Then this lady is your sister. And then you generalize not just psychologists, but it's actually general people. And so you can actually generalize the rules bottom up. And that's done, for example, with the AnyWorld system. And then there are top-down approaches that start with very general rules. For example, everybody is the sister of everybody, and that make the rules longer and more precise. Well, not everybody is the sister of everybody. It's just the other person, the first person has to be female. Yeah, and actually it helps a lot if they have the same parents. Yeah? And this way you make the rules more precise and they become more concrete and more correct. And so there are several approaches that can do this. For example, the AMY system or the routing system. Yeah. So this is the preliminaries. These are tools we're going to use in the sequel to find where our knowledge base is incomplete. So let's now come to the predictive recall assessment. So let's talk first about the recall of facts. Do we have all objects for a subject? So here's an example. Again, in the domain of scientists, this is Neil deGrasse Tyson. He's an astrophysicist, and he's married to Alice Young. You learn plenty of interesting things here. And this fact is in the knowledge base, and it's also correct. It's true in the real world as well. Now, suppose you find on the web a picture of this scientist with some other lady, young lady, of course. Yeah. So then you start to suspect maybe Neil was married to another young lady. Yeah. So that one is not in the knowledge base, but it might also be a true fact in the real world. Yeah. And so in general, the problem is given a knowledge base, given a subject, in this example is Neil, and given a relation, so married to, do we have all the objects of that relation and that subject in the real world? So for now, this missing object problem is not concerned with figuring out who these objects are, nor how many there are. We just want to know, are there any that we're missing out on? That's the missing object problem. And there are several heuristics that we can use to solve this problem to actually guess whether we are incomplete, whether we are missing something. Somebody has their microphone on. Let me check your mic. I have my mic on. Good. So here are some signals that we can use. One signal is the closed word assumption. That's the one that Simon introduced already. And the closed word assumption simply says, if there are no more wives in the knowledge base, then there are no more in the real world. Yeah. So this is basically what Neil tells his wife. Yeah. Don't worry, there are no other women in my life. Yeah. That might be a bit too conservative because we know that knowledge bases are incomplete. And so we can actually loosen that up. Another assumption is the partial completeness assumption. And that one says, look, if there is one or more wives already in the knowledge base, then most likely there are no more in the real world. Why is that? Suppose somebody creates that knowledge base and adds the astrophysicist and then adds one of the wives. Then why would that person not add the other wives as well? If somebody goes the length of creating that entity and adding some of the objects, then we assume that that person would also add the other objects. And that's an assumption. And this assumption works very well for functional relationships, that is, relationships that have a single object, such as, for example, has a birth date. If your birth date is in the knowledge base, then you have no others. Or it works also for quasi-functional relationships, like, for example, your nationality. If your nationality is on Wikipedia, then most likely you have no others, because the person who took the pain to add your nationality would probably have added the others as well. It works less well for relations that have many objects. For example, for albums of a musician. Elvis authored, like, I don't know, 100 albums or songs, right? And then, so if somebody creates the knowledge base and adds 50 of these songs, then there could well be 50 more. But so the assumption works well for relations that typically have few objects. Another signal that you can use is the popularity assumption. And that says if an entity is popular, it has no missing objects. For example, again, Elvis Presley has a very long Wikipedia page and has super many facts in Wikidata and in DBpedia and in Yago. So if there are so many facts and people took so much effort in designing that entity in the knowledge base, then you can assume that they probably made that entity complete. Whereas I myself, for example, I happen to be on Wikidata, more out of an accident, and that is for sure not complete. Simply because my popularity is nowhere near that of Elvis, which is very good. And another oracle that you can use is the no change assumption. And that assumption looks at the different versions of the knowledge base across time. So for example, assume you're looking at the states of the United States. Then you see in the first version of the knowledge base, say Yago in the year 2007, there are 5 states in the US. And then you look again at the knowledge base 2010, there are 10 states, and you look at it again in 2015, and there are 50 states. And since then, the number of states has not been changing. And then you assume that since the number has not been changing, it somehow converged to the true number. These are just heuristics, just signals. And then you can actually combine these signals and make like more complex signals. Sometimes the class membership tells you something about completeness. For example, if you're in the class of living people, then you're not missing a death date. So the fact that you're in that class tells you something. Or if you're in the class scientists and you have not published a paper, then your knowledge base is most likely incomplete. No pressure here on PhD students. You can do the same with other relations. The relations that an entity has can tell you about the completeness or incompleteness of other relations. For example, if you do not have a death place, you do not need a death date. Whereas if you have a death date and no death place, then you need one. So these are patterns in the data that can help you predict completeness or incompleteness. And then the question is, can we combine and learn these signals? And of course, the answer is yes. You can actually use these rule mining systems that we've seen before to learn weighted rules that predict completeness. So let's see how this could work. You first need ground truth. So you can, for example, ask people on the crowd, like Amazon Turk, you can ask them, do we have all wives of Elvis? And do we have all scientific articles of that scientist? And so on. And so then the crowd worker would say, yes, you have all wives of Elvis. And then you can add these signals that we've talked about before. For example, Elvis is a popular entity because he has a long Wikipedia page. You can add them as facts to the knowledge base. You simply check the length of the Wikipedia article, and if it's longer than a certain threshold, you just add he's popular. You can also add like meta predicates. For example, Elvis has one spouse on the knowledge base. You can say the cardinality is not 0 of Elvis and married to. You can even add numbers. He has one spouse, 2 spouses, and so on. And then you can use the rule miner, that is the very systems we saw before, to learn rules, but not rules about who is married to whom, but rules that try to predict whether somebody is complete. For example, you can figure out that if somebody has a spouse and that person is popular, then most likely that person is complete on their spouses. And that's a rule that you can learn in the very same way as you can learn, like you are the sister of somebody or you are married to somebody. It's a very same principle. And then you can use these rules to predict completeness. For example, you will figure out that Neil, the scientist, has one spouse in the knowledge base and he is a popular entity. Therefore, he must be complete on his spouses. Now that's one way to see it. So here are experimental results of this approach on two knowledge bases. And I'm showing this not to discuss the individual values. I'm showing this to discuss that it actually works pretty well. So you see in the columns, the different approaches: closed word assumption, partial word assumption, partial completeness assumption, popularity, oracle, and so on. And you see and the last column is if you combine these signals by a rule mining system. Now, Amy, for example. And we can see that this actually works pretty well. For some relations, it's obvious. For example, has gender. That's very simple. Either you have a gender, then you're complete, or you don't have a gender, then you're not complete. It's very simple. Has parent, the same. Either you have two parents, you're complete, or you don't, then you're not complete. For some relations, it is less obvious. For example, did you direct a film, or did you graduate from a university? And still, this approach can, with high probability, predict whether something is missing. It cannot predict which ones are missing, but it can predict whether something is missing. And so that's cool on one side, and it's scary on the other. Imagine that this algorithm was implemented by Facebook or Meta. So then one day you get a pop-up that says, it seems you have one more boyfriend that you didn't tell us about. Do you want to add that person to your profile? And then it gets scary. So as always, science can be used for good and bad. So this is the missing object problem. It is the problem of figuring out whether we are missing objects for a given subject and a given relationship. And one way to solve this is supervised learning. So you get ground truth for some subjects, and then you learn patterns that predict whether objects are missing, and you can actually do this. It works pretty well. So this is the missing object problem. Let's now first clarify maybe that Neil was or is married only to Alice, and that young lady is actually his daughter. So I wanted to put that right. So how does this help us? It helps us because if we go back to the rule mining where we wanted to predict facts, then this rule mining will predict many facts that are actually not true in the real world. It will marry lots of people. It will tell lots of people that they went to university or that they live in some places. And if we combine this rule mining with our completeness, then we can restrict the predictions to only those cases where we know that an object is missing. So we're not going to marry you if we know you are already married. And if we do that, the precision, as shown in the graph, actually rises to 1. So we predict much less things. Like at the x-axis, you see the number of predictions, but the things that we predict are true with a higher probability. So that's one use case. So let's come now to a different way of seeing the problem of completeness. And that is the question whether we have a principled lack of data in the knowledge base. Consider, for example, the relation has spouse. Consider all married people. We know that Neil is married. We know that Alice is married. And I can tell you, to show the societal impact of the work we're discussing, that entire generations are caring about whether this young man is married. Justin Bieber. I don't know whether he is, but I know people care a lot about this. So then the question arises whether all people are married. This is the obligatory attribute problem. So given a knowledge base, given a class, people, and given a relation, like married to, do all instances of the class have that relation in the real world? And we can easily think of relations that are obligatory for people. For example, everybody has to have a birthplace. So if we don't have a birthplace, then the knowledge base must be incomplete here. Everybody has to have a nationality. So that's actually a moral problem as well, that some people do not have a nationality. Yeah, thanks for attending. And then there are attributes that are not obligatory. For example, is married to, not everybody is married, or has child, not everybody has children. And knowing which attributes are obligatory in the real world is actually very helpful, because it will tell us we have a systematic problem in our knowledge base if people don't have birthplaces. Whereas if not everybody is married, it's not so much of a problem. So you may think it's a simple problem. It is not. So here is how the real world looks. So this is the set of people, and suppose the green dots are the people who are married, and the red dots are the people who are single. Yeah? So then suppose we have also the classes. So here, for example, we have the class of woman, which is a subclass of the class of people. And I'm introducing here another class, which is the class of consorts. These are people whose only job is to be married to a king or to a queen, the royal consort. And naturally, all dots in that class are green, right? Because it's their job to be married. If they were not married, they could be a consort. This is how the real world looks. Our knowledge base, first, does not store the negative facts. This is what Simon said. So the red dots go away. And second, we do not even have all the green dots, because the knowledge base is incomplete. For example, in the preceding version of Yago, only 2% of people have a nationality, which is an obligatory attribute, and only 2% of people are married, which is not an obligatory attribute. It's actually very hard to guess whether this attribute is obligatory or not. But you can do it under certain assumptions. These assumptions are that the knowledge base has to be correct. So every fact in the knowledge base is also true in the real world. So all the green dots in the knowledge base are really green dots in the real world. The classes are correct and complete. We make the partial completeness assumption. So if you have one or more objects, you have all objects. And the facts are a uniform random sample of the facts in the real world. These are, of course, all completely false assumptions. And our theorem is similarly false if the knowledge base is sampled randomly, uniformly from the real world. So the theorem starts with if false. And if the density, and then it continues, and if the density of an attribute changes when we go into an intersecting class, then the attribute cannot be obligatory. Now, what does that mean? So it says it formally also below. We're going to walk through an example. Let me first explain why we're looking to this theorem in the first place, if it is based on false assumptions. The assumptions are false, but they're sufficiently true to make the theorem work in practice. And that's what justifies this this approach. So it will work in the end. So let's see what the theorem actually says. It says that if we look into the class of people, for example, and we look into the density of the green dots, there are 2% are green dots in our class of people in the knowledge base. And we walk into an intersecting class, which is the class of consorts, which is a subclass thus intersecting, then the density increases of the green dots. And that means that the attribute cannot be obligatory for people. Why is that? If it were obligatory for people, like everybody's married in the real world, and we randomly draw people from the real world and check if they are married, then that density should not change if we look into any specific types of people. Consorts, for example, should have the same probability of being married as other people, but they don't. They have a higher probability. So the class membership has an impact on the density. And therefore, the theorem tells us that the attribute cannot be obligatory for people. Is it obligatory for women? Well, no, because if we walk into the intersecting class of women consorts, the density increases, and that means it cannot be obligatory for women. And this gives us a mechanism that tells us whether an attribute is true, is obligatory in the real world, whether all subjects have that attribute. And this works by density estimators that simply check whether an attribute changes its density. This approach is based on a number of false assumptions, but it works sufficiently well in practice. Good. So far, we've looked only into the knowledge base itself to figure out whether an attribute is missing in the knowledge base, which is actually pretty miraculous, right? So we look only at the data and we try to estimate from the data alone whether we are missing something else. Now let's look into other sources. Maybe we can use text to determine completeness. Suppose, for example, so we're changing the example to Marie Curie, chemist. Yes. Suppose you read, Marie brought her child Irene to school. How many children does Marie have? Well, at least one. But we don't know how many children she has, but at least one. Now, suppose you read this sentence. Marie has two daughters, Irene and Eve. Right? So she did have indeed two daughters. Irene, who went on to become a scientist herself, and Eve, who became a piano player. Now, I let you guess from the pictures which one is which. So how many children does Marie have? Well, at least two. You could even argue that the sentence somehow suggests that she has only two daughters and not more. Because if she had three daughters, then we wouldn't actually say she has two daughters, even though, of course, if she has three, she has two. You could even argue that she doesn't have any more children. Because if she had more children, you wouldn't say such a sentence. And that's somehow this implicit understanding that natural language sentences imply a range of assertions that are not explicitly stated. Now, of course, it doesn't follow logically that she has only two children, but it's something that we kind of imply when we say the sentence, and that's something that normal people who are not logicians actually also understand. And such implications are called implicatures. And in particular, scalar implicatures say that no more facts are true than those that are explicitly stated. So in our example, she doesn't have any more children. And this is something that gives rise to the text coverage problem, which is the problem of, given a sentence, figuring out whether it mentions all objects of a relation or not. In our example, Marie brought her child Irene to school. We can't deduce that this would be all her children. So the sentence is incomplete. Whereas Marie has two daughters, Irene and Eve, the sentence is probably complete. And the text coverage problem is classifying these two. And that can actually be done. Here's an approach. You start with the sentence, Marie brought her child Irene to school, and you use vanilla information extraction. For example, open information extraction together with a PATI system. And this system will tell you that the sentence says, has child Marie Irene. It doesn't always work, and there are error probability, but in general, this works with short sentences. This works sufficiently well. And now suppose that you use Wikidata and you figure out, look, Wikidata says Marie has two children, Irene and Eve. Yeah? So then you can figure out that the sentence is incomplete. So if the sentence mentions two entities and Wikidata as well, then for this to work, you assume that Wikidata is complete. And then again, you can use the previous approach that we've seen to justify that. And so you can actually figure out that the sentence must be incomplete in this case. And then you actually have a labeled data set, and you can train a classifier on that data set, and the classifier will tell you for every sentence whether the sentence is complete or not. And this gives interesting features. For example, here in the first yellow box, you see patterns that indicate completeness. Their daughters implies that there are no more children. Interesting. Her grandsons, his 5 children. Yeah, you wouldn't expect that there are 6 if the sentence says his 5 children. And then there are patterns that imply incompleteness. For example, her surviving sons means there could be others. Succeeded by her daughter means there could have been other daughters or other sons. In addition, a son, blah, blah, blah. So there could be other daughters or other sons. So we can actually predict whether a sentence is complete or not. So this is the part that deals with the recall of facts. How can we find out whether we are missing facts for a given subject? Now, this raises the question of how we can find out whether we actually have all subjects. And this is the missing entities problem. So assume we're building a knowledge base about scientists. Here we have the three people again, Irene, Marie, and Neil. And the missing entities problem is, given a set of entities of a given class, determine how many entities are missing compared to the real world. This raises the question of how many are there in the real world in the first place. And so how many scientists are there in the first place in the world? And that is in itself a difficult problem, yeah, because what is a scientist? Yeah, everybody with a doctorate degree is a scientist. Anybody who has published a paper is a scientist. Yeah, so that's a problem by itself. So that's a philosophical problem. We have an entire paper about these philosophical problems. Let's now stick to classes that are simple. Yeah, suppose you want to know how many countries, as accepted by the United Nations in the year 2021, are there in the world. Now, suppose we work on well-defined classes. And then you can ask this question. And the standard way to answer this question is by an approach that's called mark and recapture. And that's an approach that's actually used by biologists to figure out how many animals there are in a certain area. For example, the biologist wants to know how many ducks are living in this lake. Yeah? And so what they do is they capture some ducks, they mark them, they put a ring around their foot, and they release them. And the next day they capture them again, they capture some animals again, and they count how many of the captured ones have a ring. And from this ratio, they can determine how many ducks are on the lake. So in our example, here are the scientists from the real world. You would capture some scientists, you would mark them, you know, with a ring around their foot or something. You would release them back into the wild. Then you would capture them again, and you would naturally get some overlap of the scientists you captured last time. So here, these are the black and white scientists. So Marie Curie, we captured already last time, but there are new scientists this time, which is Carl Sagan, Hypatia, and Andrei Sakharov. And then you would say, so in our second sample, 1/4 of the scientists was marked. So you assume that the ratio of marked scientists in the real world is 1/4. Since you marked 3 scientists, you would deduce that there are 12 in total. Of course, this is not so easy. Yeah? So there are more sophisticated ways of doing it. And here is one that does it on Wikidata. First, how do we sample on Wikidata? Wikidata is actually not a monolithic knowledge base. It was created over time. And you can assume that every fact that is added constitutes a sampling of that entity. For example, you can divide time to 2 sample periods, and you find in the first period that Marie Curie is the mother of Eve, that Bertrand Russell is a humanist, that Arlene is married to Richard Feynman. And the second period, you find that Marie Curie is the mother of Irene, that Hypatia lived in Alexandria, that Carl Sagan is American, and that the Sakharov Prize is named after Andrei Sakharov. And then you can consider this samples. You consider every entity that is mentioned in these facts as if you had captured that person from the real world. And so it gives you 2 samples here of the first 3 scientists and then of the 4 scientists that follow. Now, how do we actually estimate the number of scientists from there? There are several ways to do that. So the naive way of simply saying it must be the same ratio in the sample as in the real world, that doesn't work very well. So there are several estimators here, and the most popular one, or the basic one from which many others are derived, is the good Turing estimator. And the good Turing estimator looks at the number of entities that have been seen only once. So in our example, you merge the 2 samples. We saw Marie Curie twice. We saw Bertrand Russell once, Richard Feynman once, Carl Sagan once, Hypatia once, and Andrei Sakharov once. So the number of people whom we saw once is 1, 2, 3, 4, 5. And then you assume, now this is tricky, you assume that the proportion, the fraction of items that we have not seen out of the entire population is that number over the size of the sample. So in our case, it would be 5 over the total size of the sample, 5 over 7. So let's take a simple cases. Suppose that we are sampling repeatedly and we see only faces that we have seen before. Now you keep drawing scientists, you draw them, you put them back, you draw them, you put them back, and you keep seeing only ones that you've seen already before. Then you would assume that there are no more scientists because the people keep repeating. So the F1 would be 0 because nobody has been seen exactly once. And so the proportion of people we have not seen is 0. Vice versa, if you keep sampling and each time you see a new face, then the F1 is actually equal to the total number of people you have seen, because everybody you have seen only once, everybody is new. And then you would assume that the proportion of people we have not seen, the proportion of people we have not seen is everybody. Yeah, so we are actually assuming that the overall number of people is infinite if we keep seeing new people. Now that's the idea of the good Turing estimator. And when you apply these estimators to Wikidata, you can actually see that they work pretty well, at least if the size of the sets is large. For example, here, we can apply the estimators to the number of hospitals in the world. You have some ground truth, which is the horizontal line. And the colored lines are the different estimators. And you see that they converge, like the more we sample, they converge to the true number. It doesn't work so well if you look at smaller classes, for example, cathedrals in Mexico. There the estimators converge to some smaller number, and we don't actually know for what classes it works well. Because in this paper, for example, they studied like maybe a dozen classes, but there are obviously hundreds, if not thousands. As not so clear to what degree we can actually do this. But for these specific classes, if they are large, and if there's a well-defined ground truth, it seems to work. That's pretty cool. So this leaves us with the problem of what we can do if there is no edit history. Yeah? So if the knowledge base is static, then the mark and recapture estimators will not work because we have to somehow simulate the process of sampling from the real world. So let's see an example. Suppose I'm a French scientist and I'm trying to create a knowledge base of all the important cities in the world. Paris, Lille, Marseille, Bordeaux, New York, Lyon. Is there any important city missing in my knowledge base? Well, yes, of course there are. We can tell you. But how can we see this purely from the data? So only looking at this set of entities, how can we see whether some are missing if we don't have the sampling approach? Yeah? Because they're just given upfront. And here is a way in which we can still do that. You take the number of inhabitants of each city. So suppose we have this in the knowledge base. Paris, the greater Paris area has like 13 million inhabitants. So you take the first digit of that number, that is 1, and you plot it into the histogram. You put it into the bin. Then you take the other city, Lille, I don't know, Lille maybe 300,000 people. So it gives us a 3, which is the first digit. You put it in the bin for 3. New York, 8 million people. You take the 8, you put it in the bin for 8. And this is irrespective of the scale. Whether it's 8 million or 800,000 or 80,000, it's always 8. And you put it into that bin. And you might think that this distribution should be uniform. There's no more chance that the number starts with 1 than it starts with 5. There's no reason it should start with 5 any more or less than with 1. And it turns out that this is not true. This distribution actually has to follow this line, the blue line. It's actually a logarithmic distribution. I say, why should this be a logarithmic distribution? Why is it not simply a uniform distribution? And the reason is that the population of cities grows exponentially. Yeah, so a city will grow or decrease by, say, 2% every year. And anything that grows exponentially follows what's called Benford's law. And Benford's law says that the distribution of the first digit is skewed and follows this logarithmic curve. Let's see an example. Suppose you have the inhabitants of some village, like say 1,000 people live there. And suppose it's a very productive village, which grows by 50% each year. In the first year, you have 1,000 inhabitants. You add 50%, you arrive at 1,500. You add 50%, you arrive at 2,250. So you see that you passed through the digit 1 twice. You add 50%, you arrive at 3,000 something, then 5,000 something, so you skip the 4. Then comes 7,000 something, so you skip the 6. And then comes, if you add again 50%, you arrive at 11,000. So you skip the 8 and the 9. And once you're at the 1, the game starts all over again. So you can actually see that something that grows exponentially passes more often through the digit 1 than through the others. And that's a very interesting observation that Benford actually had, because he found that in the book of logarithms, at the time logarithms were not computed with a calculator, but were stored in a book, and people actually look the logarithms up in a book. The pages with the small logarithms of the number 1 actually were used more. Like the pages were like you see that they have been used more physically than the other pages. And so Benford thought, why is that the case? And he came up with this explanation. So we can see this indeed. So here is the population in the world, and you see like in different cities throughout the world, in DBpedia, Wikidata, and Yago, and the distribution of the first digit. And you see that it follows in these 3 knowledge bases the Benford's law. The population in France likewise follows Benford's law, whereas the population in Yemen does not follow Benford's law. Is that because the people in Yemen don't like Benford's law? No, it is because the distribution that we have in the knowledge base is skewed with respect to the real world. And you can use this actually to predict not just populations sizes, but anything that vaguely grows exponentially and even where you wouldn't expect it. For example, you can apply this to the number of incoming links in Wikipedia. That also follows this Benford's law. Or the size of lakes, because lakes, if they grow in surface, they also grow in this organic way. Surprisingly, it also works for things like actors in a movie, or length of a river. And it's kind of weird why it would work there. But you can apply a statistical test and check whether the law applies. And if it applies, you can guess the parameter with which it applies. And that broadens the scope where the law can be applied. And with this, you can actually draw that blue line, and you can guess how many entities must be missing to fulfill that, to fulfill Benford's law. And that is something that gives us a minimum number of entities that must be missing. It's not the true number, but it is a lower bound of missing entities. And that's the way actually Benford's law is used, not just for knowledge bases, but also, for example, to detect frauds in credit card transactions. Because statistically, these transactions also follow again Benford's law. And if some transaction does not follow that law, like or there is a skewed distribution, then this may indicate fraud, and it's actually used to detect this. This concludes this part of the tutorial. So we have seen different types of problems for completeness, and we have seen several ways to actually guess to what degree we're incomplete. The first one is, are we missing objects in the knowledge base? So this we can do by the supervised learning of rules. So are there any more spouses for a person, for example? Does a text enumerate all objects? So Neil came with his wife, Alice. Does he have any more wives, yes or no? This can also be done by a classifier and by these maxims of conversation. And finally, once you've determined whether objects are missing, you can also determine whether entities are missing. And we saw 2 approaches. One is the mark and recapture, where we actually try to estimate how many entities are missing based on whether they reoccur across different samples. And also Benford's law can also help us here. Do you have any questions about this part of predictive recall assessment? You can also speak up later, and we also have some time in the end to discuss questions. If you don't have any question right now, I propose we move on to the next part with Shrestha.
Thank you, Fabian. Okay. So let me just share my screen. And yeah, so again, if you have any questions, feel free to interrupt. So this part of the tutorial deals with getting counts from text and KB. So before we move ahead, what exactly is count information? It can be defined as a relation between an entity and a set of entities, which is represented either as enumerations via relations like employer. So Noam Chomsky and Esther Duflo are related to MIT via the relation employer. Or it can also be expressed as a count. Basically, MIT has 1,074 employees, which is a count representation of the set of entities which are connected to MIT as employers. So why are we looking into count information? So Fabian talked about functional attributes like birthplace and married to, which are mostly stable across entities, so can be easily predicted via relation mining. For count entities, for counts, this is a bit different, such that not all institutions have the same number of employees. For this particular instance, if we take other examples like children also, not everybody has children, and also not all people who have children have the same number, right? So how do we identify these sets, or how can we predict these numbers? So we look how we can use count information for assessing recall. We will first talk about extracting count information from text. So if we have a subject and the predicate that we are after and a source, can we extract the correct count from it? We'll see the different challenges involved in the extraction. We'll also look into how count information occurs in knowledge base. What are the different variants? How do we identify and align them? Next, we look into the amount of count information that can be accounted for using these two different methods of extraction. And finally, we'll see some of these counts in action. So once we have the information, how can we use it for knowledge-based curation? Right. So counts and entities benefit from each other. Take, for example, this query, where you're looking for everybody who's employed by MIT. And if you ask a knowledge base, it would return only a handful of names. So here we just have, say, 2 entities. Does that mean that MIT has only 2 employees? Now, if we look for specifically for counts and ask the knowledge base how many employees does MIT have, then it gives us a number, but we have no insight about the entities. But we know that MIT now has 1,074 employees. However, if we can align these 2 predicates, that the employees are related to the predicate employer, then if we talk about employees of an institution, we can not only talk about how many they are in number, but also give representative entities which represent the count in the knowledge base. Knowledge base also mixes counts with standard facts. So here we have the example of Tim Berners-Lee, who has 2 children as is indicated in the knowledge base. So if we are looking to the answer of the question, how many children does Tim Berners-Lee have? Then we have the exact number as a KB fact. But who these are is unknown. Now, if we look at the same question, but for Ada Lovelace, the knowledge base does not have a count, but enumerates 3 children. Now we know that they are the children of Ada Lovelace, but we're not sure if they are complete. So count information can highlight knowledge base inconsistencies if we know the alignment between the enumerating and the counting predicates. So here we have 2 examples of Noam Chomsky and Tim Berners-Lee. As we saw earlier, the number of children predicate for Tim Berners-Lee is complete. So it is populated and we know that he has 2 children, but the names are unknown. And for Noam Chomsky, we know both the predicates. However, there is some inconsistencies. So we know that he has 3 children, but only name of the single child is known. So how do we go about extracting count information from text? We look into the problem of extracting counting quantifiers. That is, given a text about a subject and the predicate that we are after, we need to determine the count. That is the number of objects that connect subject with the predicate. So if we have Noam Chomsky and we're looking for a number of children, and we're given a particular text from Wikipedia, can we predict that the number of children is actually 3? And the task is non-trivial because we need to identify the count tokens that are present in the text. And these may not just be, they may not occur individually, right? So there might be compositional cues. And we need to take into account all of this. So the way to go about it is to label the tokens. Basically, if we have any count token, then it is labeled as count. All the others are marked as other tokens. Let's give another example where we have compositional cues. So here we have Angelina Jolie, and she has 3 sons and 3 daughters. So the correct count here would be 6, but we can only know that if we know that the 3 sons and 3 daughters are to be added, right? So they are connected by this compositional cue. Right. Also, the task is difficult because count tokens are linguistically diverse. So not only will the counts occur in text, like as cardinals, 2 sons or 3 books, but it can also occur as ordinals, like somebody's 2nd son or the author's 3rd book. It can occur in number-related terms, like twins in trilogy, or as indefinite articles. Also, we need to define how to identify compositional cues. So basically, these cues occur between consecutive counts, and they might be either commas or ands. And they are all clubbed under a single table. So the second task, once we have identified the count cues, is to consolidate these count tokens so that we can return a single answer per text, given a subject and a predicate pair. The first step is to sum up the compositional cues. And here, for example, in this sentence, we sum up twins, 1 daughter, and 3 adopted children, and not 6 children, because this is separated from the rest of the counts. Next, we select prediction per type. So we introduce the different types of counts that can occur: cardinals, number-related terms, the articles, and so on. Here we see that we have predictions, 2 predictions, and both are of the type cardinal. So we select one of them, which has the highest score. And in cases where there are multiple types, we rank them such that the cardinal gets the highest rank, followed by number-related terms, ordinals, and then indefinite articles in the last. So once we follow these steps, we arrive at a prediction, which is the final answer for the given pair. Now, how do we generate the training data? It is done by incompleteness aware distance supervision. Basically, we take input from knowledge base for a given count predicate. So if you're talking about the children, we take all the subjects which have this predicate and the count associated with it, and we take all the sentences containing cardinal mentions, which are similar to the KB count. So basically, if we have number of children, then we firstly identify all the subjects that we are going to concentrate on, and then look at all the Wikipedia pages associated with those subjects, but only take the sentences which contain the counts close to the knowledge base. So knowledge base has the ground truths. However, we do not restrict to strict equality for a number of reasons. So firstly, cardinal mentions, as we looked into, include all count tokens. And similarity does not mean equality to the knowledge base count. So we need both positive as well as negative annotations. So positive annotations are those which match exactly, and also which are lower than the 90 percentile value of the value that the predicate takes in general across all subjects. So for example, for the predicate has child, you see that for the 100,000 subjects that have this predicate, what is the 90 percentile of the child predicate? If it is around 10 children, then we remove those sentences or mark them as negatives, which have a higher child count, maybe say 100 or so. And how do we get the ground truths? So we can rely on knowledge base for the ground truth. However, we cannot take all of them at face value because of inherent incompleteness in the knowledge base, which might in turn impact the training quality. So the idea is to go after the popular entities and set an upper bound as we discussed. So the popularity can be predicted by multiple signals, and you set a threshold there. And also only look into entities which have the predicate count within the certain percentile of the knowledge base distribution for that particular predicate. And this is repeated for all the predicates that we are after. Another challenge is to go after counting cardinalities when it's 0 or the negative ones. So one way to tackle this is to do some kind of feature engineering. So you look at negation determiners like no or any. Someone had no children, and so on, or an author did not write any books, which is weird. Or you also look into non-existing existence proving adverbs like without or never. Somebody never visited a particular country. And this is done only in during the text preprocessing state, and where you look for cues in the text and then label it in fixed vocabularies like no and 0, and then use it in the final prediction task. So these are the results of the Synex method for extracting count information from text, wherein they looked into these relations and tried to figure out how many relations were they able to correctly predict any cardinality. So whether the correct quantifier was predicted, what was the coverage of the relations, so for how many entities were they able to correctly identify the cardinality, and what was the error in the prediction. And we see that for 0 predictions, it performs pretty well for relations like child and spouse, which I guess has better cues in text. Okay, so now that we know how to look for information in the text, what is the situation in knowledge bases? So the problem that we are after is to identify semantically related count predicates. And for this, we need knowledge-based triples in the form of subject, predicate, and objects. And we also would want to look into the inverse predicates. If we look into our running example, the objects Noam Chomsky and Esther Duflo are connected to MIT via the relation employer. So here the main subject is the institute MIT, which stands in relation to the set of entities. So here we would actually need to have knowledge about the inverse predicate triples. And the task would be to firstly determine which predicates are enumerating types, which are counting types, and then to find whether there exist pairs of such aligned predicates. So for the task of identification, we have the list of most frequent knowledge-based predicates. And we would want to have 2 sets, counting and enumerating. And the challenges are that the separation is not clear, right? So, and the knowledge base is usually quite messy. All predicates that store integers may not always be counts. So there might be other information in it. Not all relations with store predicates are in the form of the resources. So they might be in strings or as comma separated values, and so on. So it is a difficult task, and we cannot rely on just a single signal for identification. So one way to go about it is to use supervised classification and use multiple signals. So the first one is textual features. How do these predicates occur in natural language? And what is the, how are they used? So in the plural versus the singular form. So predicate like number of children has the noun phrase children, which is more in use than its singular form child, whereas predicates, functional predicates like birthplace or quasi-functional like nationality would be more popular in their singular forms. You can also look into the type of information of the predicates. So what are the classes that the subjects or the objects of the relation take? And the knowledge-based statistics about these predicates. So what are the number of objects per subject? Do they vary a lot across subjects and so on? What is the data type distribution? Do they always take integers, or for enumerating predicates, what are the classes that the objects belong to? The second task is then to align pairs of counting and enumerating predicates. So once you have the two sets, the task now is to find the related predicates. So here, employees in the counting predicates is related to employer, work institution, and these are in turn also related to faculty. So again, the challenge here is that firstly, that the KB facts are sparsely distributed, and also that the representation in the relation is unclean. So some institutions might use employees, some might use faculty, faculty size, and so on. And they all refer to the same thing, right? So in order to arrive at these pairs, we look into a few heuristics to rank these predicate pairs. So the first heuristic is to look at co-occurrences. So how many subjects do the pairs co-occur for? And well, this is good because for institutions, the pair employees and employer would co-occur much more frequently than the pair for employees versus employees and gold, or gold titles, or employees versus child. However, it's not robust because take the example of authors and books written, number of books written by authors, and the number of children that the author has is a co-occurring pair that might occur for a lot of authors. So the second heuristic is to also look at the value distribution. That is to look at the counts stored by the counting predicates and the number of entities that the enumerating predicates store. Again, this would not always work because of incompleteness and for large classes. So definitely for employers, you would not always have all the employees of an institute, whereas so the number of entities would always be very, very small compared to the counts that are stored there. However, it works relatively well for smaller classes. But what you could do here then is not just check for equality, but the relation in which the two numbers compare. So is there any correlation? So do for all institutes the number of employees and employer increase or remain remain the same way? Similarly, for number of children and child, do they always remain same? For how many subjects are they similar? For how many subjects are they at least 90% complete, and so on? And you could also look at the linguistic similarity of the two types of predicates. So here again, number of children is linguistically more similar to child versus work institution or employer. Here, the training data generation is difficult because you cannot automatically get the annotations, and here they use crowdsource annotation for a random subset of the predicates. Again, the challenges being that the KB predicates rarely have clean values. So yeah, it's difficult because the number of triples per subject is not same, right? So not as mentioned earlier, not all subjects will have the equal number of children, say for example, or also that for predicates with store counts, it does not automatically qualify that it's a counting predicate or predicates with store integers does not automatically qualify as counting predicate because they might be codes or IDs, and Wikidata has so many IDs. So the task here is then to present to the crowdsourced worker a predicate and 5 examples of how these predicates are used. So and then the worker will look at the predicates and mark it as enumerating or counting predicate. There are graded relevance scores for these predicates because many of these are tricky, and only those predicates are used which have scores in the higher or lower ends. So the higher ended scores are used for positive as positives, and the lower ends are used as negatives, so that predicates which are confusing are left out of the training phase. And how do we get the ground truth data for alignments? Again, here, it's difficult to get ground truth data automatically, and you need to rely on crowdsourced annotations. So just select a random subset of the pairs, and then for every counting predicate, say for example, take the top aligned predicates from the other set and present it to the crowd workers, who then give pairwise graded relevance scores. And in this way, you can get the ground truth data for predicate alignments. This is again repeated for the other way, in the other direction. That is, you have for every enumerating predicate, the top counting predicates, which are then graded by the crowd workers. So these are the precision scores of different methods that were applied for the supervised classification of the two classes of counting and enumerating predicates. As you can see, it is a difficult task, and there is room for improvement because these cues again are, though they help in predicting the two classes, it might not not be enough. And we also look at the predicate alignment scores via the normalized cumulative gains. So now that we have looked into the processes for extracting count information, how much can we get? So for counts from text, there are 173,000 new facts that were mined for the knowledge base from just 4 Wikidata properties. There were 2,000 negative assertions that were made for the 2 relations that we looked into, has spouse and has child. And 2.5 million new facts were in total extracted from these counting predicates. For the in the knowledge base, we see that there were around 12,000 predicates that were predicted as enumerating. These are across different knowledge bases. So DBpedia, Wikidata, the freebase KB, and these come from around 36,000 frequent predicates across the different knowledge bases. For the counting predicates, they are around 9,000 of them. These are a bit lower, but that's because in enumerating, you also look into the inverse predicates. And so also in counting predicates, a lot of input predicates are codes and IDs, which are removed. And finally, the number of alignments that were found in the knowledge base was around 4,000, which exist. These are quite low given that we have around 12,000 enumerating and 9,000 counting predicates, and is indicative of the sparsity in knowledge bases. So there are a number of open questions and challenges. Firstly, that as we saw just in the previous slide, that the number of alignments are very less compared to the total number of counting and enumerating predicates that we have, which hints at the scope of new predicates. So if there is any unaligned count or enumerating predicate, there's scope of introducing new predicates or missing predicates. We also see that because the types of predicates are unclean, it introduces sparsity. So there might be scope in clustering similar predicates, like the cluster faculty, staff size, employers, work institutions into a single cluster, and that increases the chances of finding alignments. Cardinality extractors for text work for single predicates. So each time you come across another new predicate, counting predicate that you want to extract counts for, you need to train your on new data. Extracting negations are difficult, so it's easier to just look into cues into the text, but you have more on this coming up in Hiba's part. Also, enumeration is difficult, as we saw. For children, it's relatively complete. However, for classes like population and books, it's usually very sparsely populated in the knowledge base. So let's go through a few examples of how these counts are can be used. So if you know the two predicates here, Here we have a demo that you can go and play with, which is a very simple SPO query system where you have an entity and you search for a particular counting predicate, either counting or enumerating, and it returns the answer for the query that is being made and also the related predicates if they exist. So this helps to identify cases where there might be inconsistencies or incompleteness. So this was queried quite some time ago, and we see that this is already updated to 3 in the knowledge base. You can also look at the value distribution of the aligned predicates and to check for incompleteness. So for example, here in Wikidata, member count and member of political party are aligned predicates. And if we look at the distribution for different subjects, what the integer counts are and what the number of enumerations are for the enumerating predicate, we see that this is highly incomplete in terms of enumerations, right? Because say, for example, for a particular subject, which has 1,500 members, only a few, 2 or 3 members of that party are there in the knowledge base. You could also use this for enhancing question answering. If you're looking for a particular attribute of an entity, say number of gold medals won by Roger Federer, even though Wikidata, or here is the DBpedia, even though DBpedia does not have the instantiations for the entity, for the predicate that you're looking after, you can rely on related counting predicates for getting your results. So even though we do not know how many gold Roger Federer won, gold is related to doubles titles and singles titles, and we can hence get the answer to this question. Right, so we are towards the end of this part of the tutorial, and the takeaways are that count information is important for recall assessment, and it comes in 2 variants of integer counts and enumerations, which can benefit from each other. We saw how to extract count information from text, which is linguistically diverse and has negations in it. We saw how count information occurs in knowledge base, how we can identify the 2 variants and also align them, and how these counts can finally be used for knowledge base curation by either highlighting inconsistencies or incompleteness, or for enhancing knowledge base question answering. So any questions? If not, then if any questions arise, feel free to write it in the chat. Otherwise, I'll hand over to Hiba.
Thank you, Shrestha. I can assume that you can see the slides and hear me. Yep. Okay. So this is the part of the tutorial where we discuss negation and knowledge bases. My name is Hiba. So let's say we want to get awards that Stephen Hawking has won, and for that we're querying Wikidata. We would receive some awards that he has won, including the Albert Einstein Medal, the Wolf Prize in Physics Medal, Prize, etc. A total of 42 awards. But what can we say about this one, the Nobel Prize in Physics? It's not one of these awards. Can we say that he didn't win it just because it's not in the knowledge base? Can we say he probably has won it, he's a popular physicist, and it's not added yet? All we can say is the knowledge base doesn't know because of the open word assumption, where we cannot assume that the absence of a certain piece of information means its falseness. All we can say is that the knowledge base doesn't know yet. It could be false or it could be unknown. Now, the problem is that existing positive-only knowledge bases are unaware of negation. So as I said, we cannot make a decision about the Nobel Prize in Physics. And one easy or straightforward solution would be, okay, let's make it aware of negation. Let's add every possible negation so that we know what's the case for something like the Nobel Prize in Physics. But if we were to do that, even for something as simple as a word of Stephen Hawking, okay, he has won dozens of awards, and then you have to assert every possible award that he did not win, and that goes into 30,000 awards. So he also never received an Oscar. He never received the NBA award, etc. So it's if you were to go for the solution, the set of negative statements is very huge, it's overwhelming. And this is just for something like awards. Now imagine even a bigger relation like spouse. So during his lifetime he was married to 2 or 3 people. Now imagine that you want to add every other person that was not married to Stephen Hawking, and that's billions of people. So it's the solution is not very feasible. Now, even with that, even with what I said that existing knowledge bases are mainly positive, we have some knowledge bases that are currently either allowing the addition of negation in some shape or form, or allowing the retrieval of some negation. And one good source for retrieving negation is collaborative knowledge bases. So in collaborative knowledge bases, you have edits and revisions that are happening every minute, and you have statements that are being deleted, and these deleted statements can be considered a source of negative statements. So if I have a statement in the 2017 Wikidata and then I don't have it anymore in 2018, I can compare and say this is possibly an interesting negation or a negation. However, with a deeper look on these, we find that 82% of these deleted statements are ontology modifications. So it's something like updating the way an entity is being expressed. So he is vegan to his lifestyle is veganism, or adjusting numerical IDs for Wikidata, like adding a prefix to the ID or something like this. So they weren't basically mistakes that have been removed. One other way of presenting negation, and this is related to Shrestha's part, it's the count predicates. So something like in Wikidata, number of children can be expressed, can express negation if the number of children is 0. However, the problem with this is not very general. So it's a handful of predicates that include numbers, but it's not, we don't have or number of spouses, etc. Another way of presenting negation is negated predicates. So predicates that are dedicated to express negation, they have negative keywords in them. For example, with Wikipedia, you have never exceeded altitude for some airplanes. With no life, which is a medical knowledge base, you have not caused by or not healed by for some diseases. But again, this is just a handful. So it's not that for every positive relation, you have a negative one. Another way of expressing is, so we know that triples in knowledge bases are SPO triples, so subject, predicate, object. You can express a negation by explicitly assigning the object to no values. For example, the information about children here again is, child with an explicit no value means this person does not have children, and it's not an unknown anymore because it's been made. And you have the deprecation rank, which is also data. I'm not sure if other knowledge bases has, mainly to leave the better state marks. So I was discussing the ways we can add negation to knowledge bases, and some knowledge bases currently allow the addition. So if you were to add them, you have a way to do that. So even some knowledge bases like Wikidata allows you to query negation using Sparkle, where you say where you assign the object explicitly to no value. So you say, give me entities that have not have no children, and in this case you wouldn't get statements that to no value, and that's advantage of the negation in knowledge bases. The limitations, however, is that they inherit the same challenges from the positive knowledge base completeness, and this is what Simon mentioned at the beginning, where incompleteness is a problem because you have incomplete sources and you have imperfect extractors, and on top of that, in the negation part, you have quasi-infinite information. So you have to validate everything and make sure that they are correct, and you have to store them and maintain them. So it's not very simple to add every possible negation to knowledge bases. And what we've seen here from the relations that we have is they cover small domains. So for number of children, you have number of children, maybe number of seats, number of stadiums, but they are not generalized to everything in the knowledge base. And there's no active collection of useful negations. So far, negations that are added kind of randomly, whatever the editor feels should be added, or positive information that has been added and then marked as an error, but it's not basically there's no like formal framework to add these negations. So to formalize the problem a little bit more, as we said, existing positive-only knowledge bases are unaware of negation. So our input is an open-world knowledge base where we're not sure that the absence of information means it's false. So here I would divide knowledge in three parts. The positive knowledge, so knowledge we know is true. Negative knowledge is knowledge we know is not true. And unknown, which is a very small portion, which means knowledge we know we don't know. So this is something like historical events that we don't have universal truth around, or death mysteries, etc. This is a very small portion. And what we discussed so far is that knowledge bases exist in the positive area. However, it does not cover it completely. So it knows some of the positive knowledge, but it doesn't know any of the negative knowledge. And in this part, we want to discuss the making the knowledge base aware of some negation. So it will still mostly know positive information, but we want it to know to be aware of some negation. And the main question in this part is what kind of negation we want it to be aware of. And the answer is useful negative knowledge. Something like Stephen Hawking never received a Nobel Prize in physics. He's a famous physicist. That's interesting. Marilyn Monroe, one of the most famous actresses in Hollywood, never received an Oscar. IBM's headquarters is not Silicon Valley. So this is the kind of negation we want to add. And for this problem, I will divide the solution into three main approaches. And for every approach, I have a couple papers or some work on that approach. But most of them, or all of them, are solving the same problem. We want to identify useful negation or interesting negation or meaningful negation. Now, the first part is using statistical inferences. So from positive statements in the knowledge base, we want to infer or produce interesting negations about entities in the knowledge base. And the first method is called the peer-based negation inference, where basically, given an entity from the knowledge base, again, it's an open world knowledge base, we identify peers and we produce candidates based on the information from these peers. We filter the correctness because, again, this is open world. So just saying that this negation or this statement is negative is not sufficient. You need to make sure that it's actually incorrect and not just missing. And after you identify your candidate negations, you want to make sure that they are useful because we want useful negations. So the output would be top interesting negative statements about the entity from the input. Now, the first step would be to identify similar entities or peers. And these can be defined in several ways. One way is to do it using classes. So saying your input is Stephen Hawking, then other peers could be people who share the same profession, so other physicists. Or you could go for a little more general way of defining peers, and that's J-card similarity. So basically predicate-object pairs shared by entities. So I have Stephen Hawking and I have a potential peer, Einstein. And now I see how many peers they share in common, and this is how close they are. So it's basically the intersection over the union of their statements. Or going even more general and shooting for latent representations like entity embeddings, where you do cosine similarity between the embeddings of your input entity and the embeddings of another given entity. And all of these can be later confounded using other ranges. For example, if you don't want to consider every other person in the knowledge base, you can say just people as popular as Stephen Hawking, and then within these, you would collect your peers. And if you can notice that the functions on top are more interpretable, so you can actually pinpoint why these entities are peers, because the peer group has a label. So these are peers because they are physicists. These are peers because they have the citizenship of the USA, etc. But are less accurate, because you could have, for example, another physicist that doesn't share anything with Hawking except the profession. So he's from a different country, different time era, different area. Like different field area, etc. And the bottom functions are less interpretable because they are more numerical. So if it's not obvious why these two entities are peers, it's not, you can't really know why, except for the cosine distance that you have. But they are more accurate because they include more and more information about the peers, and the and they contain more latent representations of these entities, so they can be more accurate. Now, at this point, the peers have been defined, or a way of defining peers using these functions. And say my input entity is Stephen Hawking in this case, and the peer is Albert Einstein, and it has been chosen using one of the functions that I just mentioned. Now, of course, he's not the only peer, you have more peers, but just for the sake of this example, I'm using one peer for my entity. And Stephen Hawking, and this is a small example, so imagine the knowledge base only know this information about Stephen Hawking, that he's Edward Hawking is his brother, and then he has won the Copley Medal. And we know some information about Albert Einstein, like his sibling, award he has won, that he likes reading and sailing. And the first step would be to just, every statement that the peer has, just move it automatically to the entity and consider it candidate negative statements. So move everything in green for Einstein to candidate negative statements for Hawking. But again, is this enough at this point? Can I just assume that whatever the peer has, so here we're assuming local closed word assumption, we're assuming closed word assumption only within the peer group. So can I just assume that these red statements are automatically correct, and now I have to find out if they are interesting or not, and that's it? Unfortunately, the challenge here is still correctness. Even within this local closed word assumption, these statements can still be absent and not incorrect. So how can I filter them further to make them more correct? Here, a simple heuristic can be used. And this is related to something Fabian has mentioned at some point, where if someone made the effort, if an editor made the effort to start adding the awards that Stephen Hawking has won, then he or she probably will add all of the awards that they have won. And we can assume that any award that has not been added to be false. However, there was no hobbies for Stephen Hawking in this. So we cannot make sure that he doesn't like reading and sailing because he doesn't have other hobbies in his positive information. So the heuristic would be to delete everything that where the relation doesn't exist, and keep everything that some object for that relation exists. And this simple heuristic significantly boosts the correctness from 57% to 84%. So at this point, I have defined the peers, I have retrieved candidates negation, and I filtered them by correctness. So the ones I still have are most probably correct. And now all I have to do is, are they interesting? Are they useful? So now it becomes a ranking problem. So I have my candidates here. So Hawking, Maya Einstein is not the sister of Stephen Hawking. He's not a citizen of the US, and he did not receive the Nobel Prize in Physics. And now I need to rank them by, or I need to score them by saliency. And for that, I need scoring features. One obvious scoring feature, and it proved to be the most powerful one, is the peer frequency, right? So how many of the peers are siblings of Maya Einstein? How many of the peers are citizens of the US? So the portion of the peer group that have the statement as positive. Other features include authority of object and predicate, so frequency of the predicate and popularity of the object, and also textual signals. So we can also include Wikipedia embeddings of these entities or of these statements. And all of these features are put in a linear regression model. So they are features to be tuned. And for this, we need labels. So we need labels for statements. Are they interesting or not? And for this case, you need annotators. So here, annotators were asked for each of these statements. Do you think it's interesting that Stephen Hawking never received the Nobel Prize? Do you think it's interesting that he's not the son of Hermann Einstein? And the annotator can say, this is interesting to me or not interesting. And the model is trained, and the features are tuned, and then you rank your candidate by predicted score. And in this case, the most interesting one of these candidates is that Hawking never received the Nobel Prize in Physics, and then he's not a citizen of the US, and then lastly that Maya Einstein is not his sibling. Now the advantages of this method is that the recall is really high. So for almost any entity in the knowledge base, you can identify peers, and you can identify candidates, and you can predict and infer. And the other advantage is canonicalization. Again, the main problem in this part is to define negation in the knowledge base itself. So it's crucial that the inferred negations are expressible in the knowledge base we have. In this case, they are, because the relations inferred are part of the knowledge base, and the entities inferred are also part of the knowledge base. The limitation, however, is correctness. So even with the ranking and the filtering, it is a best effort. It's an inference. So what is said here is that these negations are most probably correct, and they are salient, but it's still a probability. Now, the second method is the order-oriented peer-based inference, and it's based on the first method. And the main idea is basically the same, like the intuition of the method is basically the same. Can I observe peers in order to infer negations about my entity? But here, instead of using binary peers, where the entity is either a peer or not, we want to exploit the order of the peers by either exploiting the spatial and temporal data provided in the knowledge base, or some of the functions that I mentioned before, but this time rank the peers instead of just collect top 100 or top K and say, this is my like bag of peers. And one example here is my entity is Frances Arnold, and she is one of the winners of the Nobel Prize in Chemistry. And her peers are other people who has won the same prize. But in this case, they are ordered. So they are ordered, and you can see that at some positions, so in 2017, you have 3 winners. So these are peers at the same position. And then 2016, 3 winners, and 2015, also 3 winners. And they are ranked. And this is just a small portion. So you can imagine that I would go back until the beginning of the Nobel Prize in Chemistry. And one negation here is, salient negation, is that her gender is not male. And the interpretation of this, or the explanation of why this is interesting, is that unlike 9 winners out of 9 from the previous 3 years, she is not male. Another interesting negation is that she's not a citizen of the UK. And again, you have an interpretation, like 3 winners out of the out of 9 from the previous 3 years. So you have an explanation of why this is interesting. So I would stop here for a second, just make sure that you're still hearing me.
Yes.
Okay, great. So at this point, just to compare with the previous method, if I was to use the same exact entity group, etc., it was going to be Francis Arnaud again is my entity, and then you would get a group of chemists. Now, chemists, if you were using the class base, but if you were using entity embeddings, for example, it would be just closest people. So you wouldn't really know why they are close. And then you might end up with the same negation that she's not male. But it's not really obvious here. Why is it interesting? Here you have more context. It's giving you more information about the situation. So what it's saying here is that in 9 winners from the previous 3 years, she is the first female to win this award. And this one, you're not really sure why this is interesting in this context. And that's one of the main advantages of this method over the previous one. Now, how are they different other than the notion of the peerness and how they are ordered? And the other main part is how you score the statement by saliency. How can I identify that a certain negative statement is interesting? So previously it was a simple scoring function. Mainly I'm just reducing it to the peer frequency because it was proven in the previous work that it's the most powerful scoring feature. So basically, how many of these peers share a certain positive statement that she doesn't share over the total number of peers. Now with the new one, you have the new variable, which is m. M is the prefix length. So I'm not just comparing with all of the members of the group at the same time. I'm moving gradually and comparing and scoring at this point, and then scoring again at this point, and so on. And then I'm retaining the maximum score, which would be my final score. So let's go through this with a more specific example. Say my candidate statement is that she's not a citizen of the UK. And now I need to score this using the previous method and using the new method. For the previous method, it would be something as simple as two people in this group or 2 chemists are citizens of the UK out of 8. So that's 25% saliency for this statement for my entity. Now with the new one, I need to go for every position. So I would go to 2017. I have 3 winners. So out of these 3 winners, how many of them are citizens of the UK? And it's only 1 person, so that's 1 out of 3. I would move to the 2016. Now I'm reading these 2 years together. So at this position, how many people or how many winners of the Nobel Prize in Physics are citizens of the UK? That's 2/6 again, which is third again. Now I'm equal 3. I'm reading 3 years. Again, 3 out of 9. That's 1/3. At this position, you can see that the score of the statement is the same at position 2017, 16, and 15. So which one is saying more? Which one should be considered as the most salient one? And for this, the scoring function has been updated to also reward the number of peers. So the more peers I read, the better. So at this position, I only read 3 peers. At this position, I read 9 peers. So if it's the same score for both of them, I should reward the one where I read more peers. And this would end up being, for the not citizen of the UK, 2 out of 8 similar people or similar chemists for the previous method. And for the new method, it would be 3 out of 9 winners of Nobel Prize in Chemistry from the previous 3 years. Now, the advantage of this version of the method is its interpretability, which means that I have more context. I have a very clear context of why this statement is interesting, because I'm reading within an order group. This group has a label, etc. The canonicalization is again an advantage. I'm inferring from the knowledge base itself, so everything that I am inferring can be linked back to the knowledge base, no problem. The limitation, however, is recall. And here I have a question mark because not in all cases. So if I'm relying on temporal data in order to retrieve my peers, then it could be a problem for entities that don't have temporal data or don't have spatial data. So for these entities, I can't retrieve any peer groups. So it depends on the function I'm using and on the popularity of entity I have. Now, what we discussed was trying to infer negation from the knowledge base itself. Now, the second part would be, can I go to text and try to find some useful negation there? And here I would discuss two methods. The first one is the text, is the mining negations from user query log, and it's a pattern-based method. And the main idea of it is, let's use the wisdom of the crowd. Let's use what people think is interesting negations and just extract them and add them to the knowledge base. And for this, one good source is the auto-completion of a search engine. So where people frequently ask questions, and we want to try to look for frequently asked questions that are also negative. And for that, you can probe it using negated prefixes. So why didn't E, and E here is your input entity, and then you would let the auto-completion model finish it for you. And the reason the word why has been added here is that we can assume that whatever comes after why is correct, and the reason the user is asking why is just asking for the reason of that negative statement that is correct. For example, for Stephen Hawking, why didn't Stephen Hawking? And then the auto-completion model would say, get a Nobel Prize or get a knighthood, which means that he didn't get a Nobel Prize, and the person who asked is only asking for a reason. With the country, why isn't Switzerland? So why isn't Switzerland in the EU? Why isn't Switzerland in the NATO? So here we can assume that it's not a member of the EU. Now, the advantage of such method is obviously the relevance and correctness. These are the most frequently asked questions, and they were asked with the question why, which assumes somehow that, like to a great extent, that these are correct questions, correct statements, but the annotator is only asking for the reason. The limitation, however, is the recall. So you have limited access to these kind of sources, and in general, they are the most frequent ones. So they are the top questions. They aren't many for every entity. The other limitation is the canonicalization. So the goal again is to add these negations to the knowledge base. But with text, you need something in between. You need a step where you're linking the object to an entity in the knowledge base, and where you're linking the relation to a relation in the knowledge base, which in some cases does not exist. So you don't have all the relations in the knowledge base. So that's a major limitation for this kind of method. Now, the second method on textual extraction is mining text revisions. And in this case, the main goal is to create an anti-knowledge base, or AKB. And this knowledge base, this AKB, only contains common factual mistakes. So it's not meant to replace the original knowledge base, but to complement it. So you have your original knowledge base, which is positive only, and now you have your AKB, which is the anti-knowledge base, update logs. So in this case, the logs are textual. So you have a sentence that has been updated into a different sentence where only one thing was changed, either an entity or a number. So it should be either an entity swap or a number swap. In this case, for example, for Albert Einstein and the revision number 505, we had Einstein was born in Vienna. That has been changed in the next revision into Einstein was born in Ulm. So it must be that the first one, or it could be a common factual mistake. So people think that he was born in Vienna, and that's an interesting negation. And to check the correctness of these revisions, because it could be the other way around, right? It could be that it was correct and someone changed it into something incorrect. In this case, web hits are used in order to check correctness. So would we get more hits for he was born in Vienna, or would we get more hits for he was born in Ulm? And that's how correctness is being judged. Now, the advantage of this is correctness. So again, because you have human annotators in this case, you have updates that have been done carefully on Wikipedia, with the exceptions of vandalism and controversial topics, etc., which this paper takes care of. So they any entity that has been added very often or in a certain suspicious way, all of these are dropped. But for the rest of the updates, they are mostly correct. The limitation, however, is the relevance. So this is an interesting case, but most of the cases were not that interesting. So changing a year. So this happened in 1950, but not 1951. So it's not very highly useful for the for querying or some of the use cases that I will mention on the next slides. The other limitation is that the update log is being mined. However, not every update is a removal of a factual mistake. So based on an analysis that has been done in this paper, actually 60% of the updates are not factual corrections. They are either controversial topics or synonyms, so you're just changing a word for a very similar word or correcting a spelling mistake, etc. So the recall is in this case not very high. The third approach is pre-trained language models, and this is a work that its main goal is generating meaningful common sense negative knowledge using pre-trained language models. So it's a simple framework. And a first step, they want to generate corruptions, which means plausible candidate negative statements by correcting the positive ones. And the source in this case is not Wikidata or a general purpose because it's common sense, it's ConceptNet. And the second step would be to estimate the contradiction between what you just corrupted and truth. And in this case, you would use a fine-tuned pre-trained language model like BERT for common sense classification and see whether your corrupted statement, how far is it from the truth. In this case, you have a positive statement that says a horse is an expensive pet. Now we'd start corrupting either the subject or the object. You would change horse into cat or goldfish, or you would change expensive pet into expensive car. And then you would start measuring the correctness of these corruptions by submitting them to BERT and getting confidence score for these statements. Now, the obvious advantage of this is recall, because you can make as much corruptions as you want and test them and estimate their contradiction, so there's no limit to that. The correctness, however, is kind of an issue, especially with the idea of considering language models or pre-trained language models as source of knowledge. So if you are in the opinion that they are good sources of knowledge, then this wouldn't be a big deal. However, you should be aware of biases and some incorrect answers that you might get. Now, just to summarize the methodologies that I just described and the advantage and limitation for each one of them. So we first discussed the peer-based negation, so the unordered peer-based, and the advantage of this method was the relevance because of the peer frequency that we have, which is a very strong indicator of relevance. The recall is very high. You can predict negations for any possible entity. Canonicalization is not a problem because you are presenting the negations in entities and relations that already exist in the knowledge base. Correctness, however, is questionable because of the open world nature of the knowledge base. So again, it's at best, it's an inference with very high likelihood, but it's still an inference. For the ordered version of this methodology, correctness is still an issue because again, open world and inference. Relevance is very good, and I added this plus because it's not only relevant, but it's also interpretable. So you have a verbalization of why this negation is interesting. Recall is a little bit questionable, again, because if you're using temporal or spatial information in order to order the peers, then you have to guarantee that the entity is part of a certain temporal sequence or spatial sequence, and it has temporal and spatial information. Canonicalization, again, is not a problem because you are inferring from the knowledge graph itself. For the anti-knowledge base, where they infer or they mine common factual mistakes from revisions, correctness is very high because you have your evidence and you're checking it on the web, so you're checking the hits. Relevance is an issue because, again, not every update is a factual error, and not every factual error is an interesting factual error. Recall is not very high, again, because 60% of them are not are either synonyms or controversial topics or a spelling mistake fixing, etc. Canonicalization is a big issue because, again, in this part of the tutorial, the goal is to add negation to the knowledge base itself. So I should be able to link the relations I find to a relation in the knowledge base. I should be able to link the entities to entities in the knowledge base. And that's a big problem in textual work because for many of them, you cannot link them back. With the query log, it's again similar because it's also textual. So the correctness is high because these are the most frequently asked questions. Relevance is high because you have your evidence, and it's you have an evidence that this is a frequently asked question. So otherwise it wouldn't exist in such auto-completion model. The recall, however, is very low because, again, you don't have access to a lot of this data, and in its nature, it's not very rich. It's very limited. Canonicalization, again, it's a problem because of the textual nature of the extractions in this case. And the last one is the common sense using pre-trained language model. So inferring common sense negations using pre-trained language model. The correctness is questionable. It depends on whether this specific language model is a good source of knowledge or not. So it could be good. Relevance is high because of the usually the finding the contradiction between truth and the corrupted statement is very good, regardless of its correctness. It's the finding the how far is it from the truth is very reliable in this case. The recall is very high, again, because you can corrupt as much as possible as you want and measure the contradiction for as much as you want. There's no limit on this. Canonicalization is not a problem because when you're corrupting entities into other entities. So you would end up also with entities that are easily linked back to your input knowledge base. So now that we discussed the approaches, let's go a little bit briefly over some of the projects, some of the resources that you can use with that they have the main focus to find useful negations and knowledge bases or unstructured information in general. And the first tool is Wikinegata. It's a tool that is built upon the first method that we mentioned, the peer-based negation inference. It contains 500,000 interesting negations about Wikidata entities that a user can query using an entity summarization interface, where you can enter something like Albert Einstein, and then you would receive a list of interesting negations about Einstein. You would get to see his peers, you get to see why this is interesting, and many other functionalities. In the same tool, you have another interface where you can ask the question in a different way, or your query in a different way. Instead of the entity being your input, you can ask. You can do question answering using triple patterns. So you can say, give me entities that did not win the Nobel Prize in Physics. And instead of receiving random entities that this statement does not apply to, you would get actually interesting physicists who did not win the Nobel Prize in Physics. The second tool is a game. It's a guessing game. But it's a guessing game with negations as clues, with interesting negations. So you would be given 3 entities, and you should guess which one of these entities these clues apply to. However, the entities are valuable negations instead of the traditional case where you would get positive clues. So instead, he is of a certain nationality, you would get that he isn't. Or he did win an award, you would get that he didn't win a certain award. So at this point, we already know who did not win the Nobel Prize in Physics, and he's not German, and he was not educated at Trinity College. So in this case, the answer is Stephen Hawking. A third data set in this case is the anti-knowledge base. I discussed the idea of the method and how these negations were retrieved using Wikipedia log. The data is available upon request, so you can request it from the author and they would share it with you. The data contains 116,000 likely mistakes where people either swapped an entity or a number, and then you would get the statement before the revision and then after the revision, and then the entity that has been swapped would be marked, and then you have a confidence score of how confident are we that this is actually a factual mistake and not something else. Another data set, but this time on common sense negation, is Anion. It contains 500,000 or more than 500,000 if-then rules where logical negations are inferred from original positive information. So in this case, if X wears a mask, then X is seen as responsible. What is the opposite of that? Is that if X doesn't wear a mask, X is seen as carefree, etc. The data is available at this link. And the last one is an online platform that we all know, we all use for booking hotels and such, is the Google hotel search. So usually, normally, you're booking a hotel, and then you would check the features, and then you get that this hotel, it would offer me Wi-Fi, it has a bar, it has a front desk, etc. But the thing that we're starting to see now is that also negative features are useful in this case, because I want to know what doesn't it offer explicitly. And in this case, the Google hotel search is telling you that this hotel does not have a pool, it doesn't allow pets, it doesn't have a spa, etc. And this sort of negations are usually retrieved from the websites of the hotels themselves, or from a third-party services like Booking.com, or from user reviews. And then you can try it for yourself. Now, the takeaway from this part is that, as we've seen, current knowledge bases lack negative knowledge. We have seen a rising interest in the explicit addition of negation to open world knowledge bases and a number of approaches, and also a number of projects and tools and data sets. We have seen a few examples why negation can be highly relevant in applications like entity summarization or commercial decision making, like when you're booking a hotel, and this also generalized to online shopping in general. And also QA systems, where if I ask, is Switzerland a member of the EU, I should be able to get a definite answer from the knowledge base that it's not. It's not this isn't an absent statement. It is in fact negative. And we've seen that methodologies to find such negations include statistical inferences, as we've seen in the peer-based ordered and unordered version, peer-based negation. Text extraction, we've seen it in mining update logs, but also mining query logs, and the pre-trained language models that generated interesting common sense negations and common sense knowledge bases. Thank you for your time. Thank you for listening.
Last part, which is relative completeness and the wrap up. So far, we've implicitly assumed a gold yardstick, namely reality. So the questions we are asking were, do we have all the Turing Award winners, or how many of the Nobel Prize winners do we have? However, this gold yardstick is not always relevant or even well defined. So I think, do we have all humans or all companies or all telephone booths in the world? It's certainly possible to define what is human, what is telephone booth, but it's largely not relevant. And some concepts are not even well defined. So all theories or songs or locations. Locations are especially ill-defined because you can always subset spatial locations or have an infinite amount of points. So instead, in this part, we look at pragmatic silver yardsticks. We don't ask, do we have everything from reality, but how much do we have from a textual source? Or how well are some entities covered in comparison with other entities? Or how well does a knowledge base support queries? So how useful is a knowledge base? And let's look at the first one. How much textual information does a knowledge base cover? The yardstick here is a descriptive text. So here on the left-hand side, we see a Wikipedia paragraph about Ada Lovelace. On the right-hand side, we see a knowledge base entry, Wikidata about her. And the question is certainly sensible, how much of the text is covered in a knowledge base? The challenge being, how do we measure it? So how do we compare this unstructured text with the structured knowledge base? And there are some works that have tried that. So one is here by Dalby and others, Tuckle 2017. So they did that for common sense knowledge in a science domain. So on the left-hand side, they used a text corpus of millions of sentences, extracted triples from that with open information extraction, and then checked how many of these triples were contained in a knowledge base. And they used that as an estimate. So the graphic on the right-hand side shows that the overlap of the sample of facts B that they aim to cover and their knowledge base C, the overlap is the area A. They use that overlap as an estimate of how much of all the facts that are relevant to science the knowledge base covers. And with that estimate, they arrived at a number of 23% recall, which has many shortcuts in this computation, but at least it's a way to get a concrete number. So 23% recall for their domain of interest. Another approach is comparing Wikipedia with a knowledge base DBpedia. So this work by Ghosh and others from last year. So they used a large scale a corpus of extractions from Wikipedia text, the OPEC corpus, in particular 6 million assertions where both arguments of the triples were disambiguated to entities. And then they checked how many of these are contained in DBpedia or how many of these can be captured in DBpedia. And the first question, how many can be captured in DBpedia? That's what we refer to as schema recall. This is illustrated here at the top. So from in the light blue, we see from all the open information extraction triples, how many can be fully expressed with a single triple? That's 29%. How many can be partially expressed by a triple in DBpedia? In other words, the semantics of the relations are not the same. Maybe born in versus lives in. And 40% of the OpenIE triples cannot be captured by a single triple. And then the other colors refer to more complex expressions. So for example, at the bottom, we see that sometimes a single triple is not enough to capture something in a knowledge base in DBpedia. So this textual triple Coral Fang was released by Sire Records in 2003. That requires 2 knowledge base triples, or there can be even more complex formulas. So Garrett Davis was a representative from Kentucky. This actually requires a disjunction because there are 2 possible ways how this could be modeled in knowledge base, or we can even require existential quantification. The message being here, about 30% of the information from text could be straightforwardly captured. The rest was more complicated. It's about the schema recall. On the other side, we have the instance recall. So how many of the things that could be captured were also captured. And again, let's focus here on the top row. What could be fully expressed of that, 27% were also present in DBpedia. Another 23% were partially present. For example, because it was a conjunction where only one of the conjuncts was present, and 50% of the OpenIE triples were not present in DBpedia. Again, there are many shortcuts in this computation, but it's a way to get concrete numbers, how much of text is contained in a knowledge base. Yet another work by ourselves looked at the temporal development. So how does knowledge base coverage increase over time? So here the method to link text and knowledge base is based on a distant supervision assumption. So we just assume whenever there's a hyperlink in Wikipedia, it's an entity of interest, and we ask how many of the entities of interest also occur in the knowledge base with a single triple for that entity. So for example, in the Ada Lovelace article, British and Charles Babbage are hyperlinked entities. And we find that British, which links to United Kingdom is present for Ada Lovelace, and Charles Babbage is present. So it's a common distance supervision assumption. We don't look at the predicates, we just look are the entities present. And once we have this method to describe coverage, we can look at the temporal development. And this is a plot how the temporal coverage of Wikidata has changed over time since 2012 for 2 sample entities, and Turing, Ada Lovelace, and for a larger sample of 234 entities. So how many of the hyperlinked entities from today at each time point are present in the Wikidata entity page? And we see that there's a continued progress. For the popular entities, it's a steep progress in the beginning. They were captured early, and later on not much more was added, but for the bigger sample we see a steady progress. What this plot hides that the absolute coverage is still low. So this is all normalized with respect to what is present as of 2020. But from all the hyperlinked entities in Wikipedia, only about 5 to 10% are present in Wikidata as well. Next, let's look at relative coverage. How well is one entity covered with respect to another? Maybe I'll skip over that in the interest of time. We're slightly behind schedule. And just describe the last method. So how well does the knowledge base support queries? That's another way to measure recall. And this replaces the question of is the knowledge base complete with the question is the knowledge base useful? And the usage here being querying. So one work by Hopkins and al. From 2018. This was work done inside Amazon. So they had access to the great resource of Alexa query logs. They looked in particular at entity property queries, value lookups. So give me the height of Barack Obama, or give me the birth date of Donald Trump, and so on. And what they did, they tried to predict which properties need to be present on an entity in order to answer 95% of the queries about an entity successfully. And the challenge here being that for most entities, there's not enough query log data, so they need to interpolate from related entities. And they used peering, similar as what Hiba presented. So they looked at entities via their classes. So they aggregated all the queries that were asked about football players and all the queries that were asked about politicians. Entity can be part of multiple classes. So they then use a neural model to merge these query profiles across classes, and could then use this predicted query log on an unseen entity to estimate how complete the information is. And so in particular, one number from the paper is that for an unseen sample of entities, they could predict that 58% of the data was currently in the Amazon knowledge base, which was needed to answer 95% of the queries. And one can again also look at the temporal development. So how well do knowledge base support queries over time? So this is based on 300 questions from search engine query logs, AOL, Bing, and Google. And based on a human annotator, so for each of these 300 queries, the human annotator went to the knowledge bases and checked since can the knowledge base answer the query, and if so, since when? And here are some examples at the bottom. So how old is Dustin Pedroia? This could be answered by Wikidata since May 18, 2017, because on that date, the birth date was added. Or where is Italian job filmed since October 15, 2015. On that day, the filming location was added, and so on. And then again, we can plot how the answerable queries change over time. On the left-hand side for Wikidata, on the right-hand side for DBpedia. And we see again a steady progress. So the knowledge base support more and more queries over time. We see a minor leveling off, so there's steeper progress in the beginning, but there's no systematic plateauing or so. So this indicates that presumably knowledge bases have potential to increase their utility over time. And to wrap up part 5, relative recall, real-world recall is not always measurable and or relevant. So alternative yardsticks to measure knowledge base coverage are text, so how much from text is covered in the KB, related entities, so how much is covered on one entity compared with others, and how well does the knowledge base support queries or usage. And especially with the usage query logs, the logical next step would be to design a cost-benefit framework where we can say where should we complete our knowledge base first, which is presumably also what was done at Amazon, but yeah, we don't have information what happens internally. With that, let me wrap up the tutorial. So the main takeaways are knowledge base are incomplete and limited on the negative side. Predictive techniques for completeness work from a surprising set of paradigms, both supervised paradigms, but also interesting other techniques like species sampling or Benford's law. Count information is a prime way to gain insights into completeness and coverage. So if you can find counts inside the knowledge base itself or in text, then that's an excellent way to assess recall. Knowledge bases are especially lacking on the negative side, and salient negations can be heuristically materialized, either using text resources, edit history, or inference from peers. And relative completeness is a tangible alternative to absolute notions of completeness, especially when a set of interest is hard to define or not all entities are of interest. So we want to give you a recipe along how to do recall assessment for a resource of your interest. So we can distinguish two cases in the ab initio KB construction. So you're building a new knowledge base, then our suggestion would be that you intertwine the data and metadata collection. So as you collect the data for a knowledge base, you also collect how complete the data is. If humans insert the data, then that means tool support, so that they not only write the statements, but also write, okay, now I inserted all the Nobel Prizes, or now I inserted all the academic degrees for Einstein. If you're doing automatic extraction, then you can use the techniques presented by Fabian and Shrestha for learning from the extraction context, how likely the information is completed or automatically extracted. If on the other hand, you work in a KB curation project, so you're given an existing knowledge base, and the suggestion would be to, if available, exploit KB internal or textual cardinality assertions, because if these are available, that's a prime way to see how complete the knowledge base is. Otherwise, inspect statistical properties on density or distributions, or compute overlaps on pseudo-random samples, the species sampling idea. We see a set of open research questions, which this community is very well positioned to tackle. So one area where we think more research is needed is to relate the different notions of completeness, in particular entity completeness, property completeness, and fact completeness. Sometimes they can be expressed via each other. So do we have all entities of a certain type? Well, types can also be expressed via facts. And so how are these notions related, and can one be used to infer the other? For the negations, a recurring issue is distinguishing salient negations from modeling issues. So often negations just occur because something is reformulated, or because there are ambiguities, whether someone is a computer scientist or an informatician and so on. So that problem deserves more attention. Recent topic of much interest are pre-trained language models and knowledge extraction from them. So we haven't seen yet good work that estimates the coverage of how much knowledge is in pre-trained language models and where should they not be used to extract knowledge. And cost-benefit techniques to identify the most valuable areas for recall improvement. Also an interesting topic for future research. So to wrap up the wrap-up, knowledge bases are major drivers of knowledge-intensive applications. We have severe limitations concerning completeness and coverage awareness. And in this tutorial, we've given you an overview of the problem, techniques and tools to obtain an awareness of completeness and coverage. And all tutorial materials available at this website, link shown at the top. And yeah, we look forward to your comments and questions now, or also send us an email later. Thank you and have a nice day.